July 14, 2015. After 9 years of travel across 3 billion miles of space, a grand piano-sized spacecraft hurtled past Pluto at over 58,000 kilometers per hour. For just a few precious hours, humanity got its first close-up look at a world that had been nothing more than a fuzzy blur for the entire history of human civilization. The images were extraordinary: a heart-shaped region of frozen nitrogen, mountains made of water ice as hard as steel, a thin, hazy atmosphere tinted blue by organic compounds, signs of geological activity on a world so cold that nitrogen freezes solid on its surface. It was one of the greatest achievements in the history of space exploration, and we will probably never go back. 4.24 light-years away, orbiting the nearest star to our Sun, there's a planet called Proxima b. It's roughly Earth-sized. It orbits in what we call the habitable zone, where liquid water might exist on its surface. It theoretically, harbor life. And we may never reach it, not in your lifetime. Not in your children's lifetime, possibly not ever. Today, we're going to understand why. Not with speculation, not with science fiction dreams, but with physics, engineering, and the hard limits that the universe has placed on what's possible. This is going to be comprehensive, it's going to be detailed, and it's going to be based entirely on reality. Let's begin with the triumph that taught us about the tragedy. On January 19, 2006, a spacecraft named New Horizons lifted off from Cape Canaveral, Florida, atop an Atlas V rocket. It was bound for Pluto, a world so distant that sunlight takes over 5 hours to reach it. A world that, at the time of launch, was still officially considered the 9th planet of our solar system. New Horizons was built for speed. At the time of its launch, it was the fastest spacecraft ever sent from Earth. It crossed the Moon's orbit in just 9 hours, a journey that took the Apollo astronauts 3 days. It was designed to reach Pluto before its thin atmosphere could freeze and collapse onto the surface, an event some scientists fear might happen within decades. But even at those extraordinary speeds, the journey took 9 years. 9 years. Think about that for a moment. In 2006, YouTube had just launched. Facebook was still exclusive to college students. The iPhone didn't exist yet. By the time New Horizons reached Pluto in 2015, the world had transformed. An entire era of human history had passed while this spacecraft crossed the outer solar system. The journey wasn't passive. In February 2007, just over a year after launch, New Horizons made a critical flyby of Jupiter. This wasn't sightseeing. This was a gravity assist, using Jupiter's immense gravitational field to accelerate the spacecraft by an additional 4,000 meters per second. Without this boost, New Horizons would have arrived at Pluto years later, if at all. For most of the journey, the spacecraft was in hibernation mode. Its systems powered down to conserve energy and reduce wear on components. Engineers would wake it up periodically to check systems, perform course corrections, and run tests. Each of these wake-up calls required sending a signal across hundreds of millions of miles of space, waiting hours for the signal to arrive, then waiting hours more for confirmation that the spacecraft had responded. As New Horizons approached its target, the excitement built within the scientific community and among space enthusiasts worldwide. Finally, on July 14, 2015, the moment arrived. New Horizons made its closest approach to Pluto, passing just 12,500 kilometers above the surface. The images began arriving immediately, though immediately is a relative term. When you're dealing with a spacecraft 4.5 billion kilometers from Earth, each signal took 4.5 hours to make the journey. And because New Horizons was busy collecting data during the flyby, it couldn't transmit everything in real time. The spacecraft stored the information on its recorders to be slowly transmitted back to Earth over the following months. What those images revealed was astonishing. Pluto wasn't the dead, cratered world many scientists had expected. Instead, they found a complex, geologically active world with diverse terrain. The heart-shaped region, officially named Tombo Regio after Pluto's discoverer, showed vast plains of nitrogen ice with no impact craters, meaning the surface had to be, geologically speaking, very young, perhaps less than 100 million years old. There were mountain ranges made of water ice, reaching heights comparable to the Rocky Mountains. There were features suggesting possible cryovolcanoes, erupting not lava but water, ammonia, or methane. There was a surprisingly complex atmosphere, with haze layers extending 100 kilometers above the surface, and there were questions. So many questions. What drives the geological activity on this frozen world? What's the composition of those strange, dark regions? How does the atmosphere behave? What lies beneath the surface? Is there a subsurface ocean, as some evidence suggests? But New Horizons couldn't answer most of these questions. Because it didn't stop at Pluto, it couldn't stop. When New Horizons passed Pluto, it was traveling at 58,536 kilometers per hour relative to the dwarf planet. That's 16.26 kilometers per second. At that speed, you could travel from New York to Los Angeles in 4.5 minutes. This speed wasn't a choice, it was a necessity. To reach Pluto in 9 years required this enormous velocity. But that velocity came with a consequence. New Horizons had to keep moving. The spacecraft had a limited window of close observation. For a few hours, it gathered as much data as its instruments could collect. It took hundreds of photographs. It measured surface composition with spectroscopy. It studied the atmosphere. It collected data on Pluto's moons Charon, Nix, Hydro, Kerberos, and Styx, and then it was gone, hurtling away into the outer solar system, never to return. The data it collected, extraordinary as it was, took over 15 months to fully transmit back to Earth, even at radio frequencies traveling at the speed of light, and even using NASA's most powerful receiving antennas, the process was painfully slow. The spacecraft was so far away that its radio signals, by the time they reached Earth, had a power of less than 1/1000th of a billionth of a watt. It's remarkable we could receive them at all. New Horizons continued its journey into the Kuiper Belt, the region of icy bodies beyond Neptune's orbit. On January 1, 2019, it flew past another object, a strange, snowman-shaped body named Arrokoth. This became the most distant object ever visited by a spacecraft from Earth. As I speak to you now, New Horizons is over 8.6 billion kilometers from Earth, continuing to move outward at about 3 astronomical units per year. It will eventually leave the solar system entirely, join Voyagers 1 and 2 as humanity's ambassadors to the galaxy. But its mission to study Pluto is complete. That brief flyby is all we'll get, unless we go back. Despite the success of New Horizons, Pluto remains profoundly mysterious. We saw one hemisphere in detail during the flyby, but the other hemisphere was in darkness. We saw the surface a single moment in time, but Pluto has seasons spanning centuries. We detected geological activity, but we can't watch it happen. We found evidence of a possible subsurface ocean, but we can't confirm it. To truly understand Pluto, we would need an orbiter. A spacecraft that could arrive, decelerate, and enter orbit around the dwarf planet. Such a mission could observe Pluto continuously, watching for changes over months or years. It could study the atmosphere in detail as it interacts with the solar wind. It could use radar to probe beneath the surface. It could study all 5 moons comprehensively. It could answer the questions that New Horizons raised but couldn't resolve. The scientific return from such a mission would be extraordinary. Pluto is a window into the formation of our solar system, a pristine sample of the materials that built the outer planets. Understanding its geology, chemistry, and possible subsurface ocean would inform our understanding of similar worlds throughout the Kuiper Belt and beyond. So why haven't we proposed such a mission? Why isn't there a Pluto orbiter in development? The answer is both simple and profound. Because we can't. Or more precisely, because the physics and engineering challenges are so formidable that such a mission, while theoretically possible, is practically beyond our current capabilities and likely to remain so for the foreseeable future. To understand why, we need to talk about the fundamental problem of space travel, we need to understand the rocket equation. And we need to confront the harsh reality that the universe doesn't care about our dreams of exploration. It operates according to laws that we cannot negotiate with or overcome through clever engineering alone. Let me show you exactly what those limits are. In 1903, a Russian scientist named Konstantin Tsiolkovsky derived an equation that would define the limits of space travel for the next century and beyond. It's called the Tsiolkovsky rocket equation, and it's brutally simple in its implications. The equation tells us the relationship between a velocity change a rocket can achieve, what we call delta V, and the amount of fuel it must carry, and the relationship is exponential. Here's the fundamental problem. Fuel has mass. To accelerate a spacecraft, you need to accelerate the fuel along with it. But that means you need more fuel to accelerate the first fuel, and then more fuel to accelerate that fuel, and so on. The result is that the mass of fuel required grows exponentially with the desired velocity change. It's not linear, it's not even quadratic. It's exponential, and exponential growth gets out of hand very, very quickly. Let me give you a real-world example. The space shuttle, at launch, weighed approximately 2,000 metric tons. That's the weight of about 1,300 cars. Of that 2,000 tons, about 1,900 tons, 95% was fuel. Only 100 tons was the actual orbiter, payload, and structure. And the space shuttle was only going to low Earth orbit, a mere 400 kilometers above the surface. It required 95% of its mass to be fuel just to reach that relatively modest altitude. Now, the velocity change, the delta V required to reach low Earth orbit, is about 9.4 kilometers per second. That's already an enormous speed, but to reach Pluto, the delta V requirement for a flyby mission like New Horizons, using gravity assists, is about 16 to 17 kilometers per second. But remember, New Horizons flew past Pluto, it didn't stop. To actually enter orbit around Pluto, a spacecraft would need to decelerate from that high speed. The total delta V requirement for such a mission, accelerating to reach Pluto in a reasonable time, then decelerating to enter orbit, would be somewhere between 25 and 30 kilometers per second. Let me put that in perspective. If we scale up from the space shuttle's 95% fuel ratio, a spacecraft attempting to orbit Pluto would need to be something like 99% fuel. But that's not enough, because the rocket equation is exponential. The true ratio would be even worse. In practical terms, to send even a small orbiter to Pluto, something comparable to New Horizons, for 178 kilogram mass would require a rocket many times larger than anything we've ever built. We're talking about a launch vehicle the size of a skyscraper, just to send a compact car's worth of instruments to Pluto. And that's before we consider other factors, power generation, for instance. At Pluto's distance, solar panels are essentially useless. The sun provides only about 1,000 the energy provides at Earth. New Horizons used a radioisotope thermoelectric generator, essentially a nuclear battery, that generates electricity from the decay of plutonium-238. These RTGs are expensive to produce, limited in availability, and politically controversial. An orbiter would need power for years, not just hours. It would need power for communications, for instruments, for the occasional course correction. The power requirements alone add mass, which requires more fuel, which adds more mass, in a vicious cycle that the rocket equation makes exponentially worse. This is the tyranny of the rocket equation. It's not just an engineering challenge. It's a fundamental constraint imposed by physics. Given these brutal constraints, you might wonder how we managed to send New Horizons to Pluto at all. The answer lies in two clever pieces of orbital mechanics: the Oberth effect and gravity assists. The Oberth effect is a counterintuitive principle discovered by German physicist Hermann Oberth in 1929. It states that a rocket burn is most efficient when performed at the highest possible velocity, deep within a gravity well. Here's why this matters. When you burn fuel to increase your velocity, the kinetic energy you gain is proportional to the square of your velocity. So if you're already moving fast, the same fuel burn produces more energy gain than if you were moving slowly. New Horizons took advantage of this by launching from Earth with a powerful rocket that gave it the highest departure velocity ever achieved. It was already moving at high speed relative to the Sun when it started its journey, making its fuel use more efficient than a slower departure would have been. But even with the Oberth effect, New Horizons needed help. That help came from Jupiter. A gravity assist, also called a gravitational slingshot, uses a planet's gravity and orbital motion to alter a spacecraft's velocity without expending fuel. As New Horizons approached Jupiter, it fell into the giant planet's gravity well, accelerating as it fell. But the trajectory was carefully planned so that it would pass behind Jupiter in the direction of Jupiter's orbital motion. From Jupiter's reference frame, New Horizons came in fast, whipped around the planet, and departed at roughly the same speed it arrived. But from the Sun's reference frame, which is what matters for the spacecraft's trajectory through the solar system, New Horizons stole a tiny bit of Jupiter's orbital momentum. Jupiter slowed down by an imperceptibly small amount. New Horizons sped up by 4,000 meters per second, that gravity assist was essential. Without it, New Horizons would have arrived at Pluto years later, or would have required a much larger rocket to achieve the same arrival time. But gravity assists have limitations. You can only use them if a planet is in the right position along your trajectory. Jupiter, fortunately, was aligned favorably in 2007, but these alignments don't happen on demand. They depend on the orbital positions of planets, which means launch windows can be years or even decades apart. For a Pluto orbiter, a gravity assist wouldn't help with the deceleration problem. You can use a planet's gravity to speed up or change direction, but you can't use it to slow down relative to your target unless there happens to be another large body in just the right position, and there isn't. Beyond Neptune, there are no large planets to use for deceleration. This means a Pluto orbiter would need to carry all the fuel necessary to decelerate itself, vastly increasing the mass penalty and making the mission exponentially more difficult. Let's talk specifics. What would it actually take to send an orbiter to Pluto? First, the spacecraft itself. Let's assume we want an orbiter with the same mass as New Horizons, about 478 kilograms, including instruments and an RTG for power. This is a modest payload, but it could carry a respectable suite of instruments: cameras, spectrometers, radar, magnetometers, plasma detectors. Second, the transfer time. New Horizons took 9 years to reach Pluto using a direct, high-speed trajectory with a Jupiter gravity assist. An orbiter would likely follow a similar path, meaning we're looking at roughly 10 to 15 years of flight time, depending on the specific trajectory and whether favorable planetary alignments are available. Third, and most critically, the deceleration burn. When the spacecraft reaches Pluto, it would be traveling at roughly 12 to 15 kilometers per second relative to Pluto. To enter orbit, it would need to slow down to orbital velocity, which at Pluto's low gravity would be only about 0.8 kilometers per second for a reasonably close orbit. That means a delta V requirement of 11 to 14 kilometers per second for the orbital insertion burn alone. Using the rocket equation with realistic rocket propellants, this would require the spacecraft's mass before the burn to be roughly 10 to 20 times its mass after the burn. If we want a 478 kilogram spacecraft in orbit, we'd need to send something like 5,000 to 10,000 kilograms to Pluto, most of which would be fuel for the deceleration burn. But remember, we also need to accelerate that 5,000 to 10,000 kilograms to reach Pluto in the first place. Using the same rocket equation calculations, we'd need a departure mass from Earth orbit of perhaps 50,000 to 100,000 kilograms or more. For comparison, the Apollo Command and Service Module, which went to the Moon and back, had a mass of about 30,000 kilograms. We're talking about sending 2 to 3 times that mass to a destination 10,000 times farther away. The rocket required to launch such a mission would be enormous, likely larger than the Saturn V that sent astronauts to the Moon. We're talking about a development cost of billions of dollars just for the launch vehicle, before we even consider the spacecraft itself. And then there's the development timeline. A mission of this complexity would require a decade or more of development before launch. At the flight time, and we're looking at a mission that would take 25 to 30 years from initial concept to arrival at Pluto. The cost, conservative estimates suggest $3 to $5 billion at minimum. More realistic estimates, accounting for development overruns and mission operations over decades, could push the cost to $10 billion or more. For context, the entire budget of NASA's Planetary Science Division is currently about $3 billion per year. A Pluto orbiter would consume multiple years' worth of that budget, meaning dozens of other missions would need to be cancelled to make it possible. And what would we get for that investment? Detailed study of one dwarf planet and its moons. Important science, certainly. The when weighed against alternatives: missions to Mars, Europa, Enceladus, Titan, missions to study near-Earth asteroids, missions to search for biosignatures on exoplanets. A Pluto orbiter struggles to justify its enormous cost. This is why no space agency has seriously proposed such a mission. It's not impossible in principle, but it's impractical to the point of being functionally impossible given current priorities, technologies, and budgets. Perhaps you're thinking, there's a better way. What about alternative propulsion systems? What about ion drives, which are far more efficient than chemical rockets? What about nuclear propulsion? Let's examine these options realistically. Ion propulsion works by accelerating ions electrically charged atoms using electric fields, then expelling them at extremely high velocities. Because the exhaust velocity is much higher than chemical rockets, ion drives are far more fuel efficient. They can achieve the same delta-V with much less propellant mass. NASA's Dawn mission, which visited the asteroids Vesta and Ceres between 2011 and 2018, used ion propulsion to great effect. Dawn was able to orbit one asteroid, leave orbit, travel to another asteroid, and enter orbit there, something that would be completely impossible with chemical propulsion given the spacecraft's modest size. So why not use ion propulsion for a Pluto mission? The problem is power. Ion drives require significant electrical power to accelerate those ions. Dawn used solar panels to generate that power, which worked fine in the inner solar system. But at Pluto's distance, solar panels would generate only about 1,000th the power they generate near Earth. You could use nuclear power instead, an RTG like New Horizons carried, or potentially a nuclear reactor capable of generating more power. But these systems add significant mass, and we're back to the rocket equation problem. The more mass you add for power generation, the more fuel you need, exponentially. Moreover, ion drives produce very low thrust. Dawn's ion engine produced to about 90 millitons of thrust, roughly equivalent to the weight of a few sheets of paper. This is fine for missions where you have months or years to gradually build up speed. But for a mission to the outer solar system, low thrust means longer flight times. And longer flight times mean more mission duration, more cost, more risk of component failure. Realistic assessments suggest that even with advanced ion propulsion and nuclear power, a mission to orbit Pluto would still take 15 to 20 years or more from launch to arrival. The technology helps, but it doesn't solve the fundamental problem. What about nuclear thermal or nuclear pulse propulsion? These concepts use nuclear energy more directly to heat propellant or to create thrust through nuclear explosions. Nuclear thermal propulsion, where a nuclear reactor heats hydrogen to extreme temperatures and expels it for thrust, could theoretically offer better performance than chemical rockets while still providing reasonable thrust levels. NASA has studied these concepts since the 1960s, but nuclear thermal propulsion still faces the rocket equation. It's more efficient than chemical propulsion, but not efficient enough to make a Pluto orbiter easy. And it adds the political and safety challenges of launching nuclear reactors into space, which remain contentious decades after the technology was first developed. Nuclear pulse propulsion, the idea of propelling a spacecraft by detonating nuclear bombs behind it, could, in theory, achieve even better performance. But this concept, studied under Project Orion in the late 1950s and early 1960s, faces overwhelming political obstacles. The Partial Nuclear Test Ban Treaty of 1963 prohibits nuclear explosions in space, and there's zero political will to change that. Nuclear pulse propulsion remains a theoretical curiosity, nothing more. The hard truth is that no propulsion system we can currently build or seriously contemplate building in the near future makes a Pluto orbiter practical. The physics is just too unforgiving, the distances are too vast, the energy requirements are too high. And Pluto, remember, is in our own solar system. It's effectively next door compared to our next topic. Because if Pluto is difficult, Proxima b is impossible. 4.24 light-years, that's the distance to Proxima Centauri, the nearest star to our Sun. Proxima b orbits that star. What does 4.24 light-years actually mean? Let's break it down. Light travels 299,792 kilometers per second. That's fast enough to circle the Earth's equator 7.5 times in 1 second. At that speed, light takes about 1.3 seconds to reach us from the Moon. It takes about 8 minutes to reach us from the Sun. A light year is the distance light travels in 1 year. That's 9.46 trillion kilometers. And Proxima Centauri is 4.24 of those light years away. The total distance is about 40 trillion kilometers. That's 40 trillion kilometers. The human brain isn't really equipped to grasp numbers that large, so let me give you some scale comparisons. If the distance from Earth to the Moon 384,000 kilometers were represented by 1 centimeter, then the distance to Proxima Centauri would be about 10 kilometers. That's the distance you might jog in an hour if you're in decent shape. If you could somehow drive to Proxima Centauri highway speed, let's say 100 kilometers per hour, how long would it take? About 48 million years. That's longer than the entire history of the primate lineage that led to humans. Remember New Horizons, the fastest spacecraft ever to launch from Earth? At its speed relative to the Sun, it would take about 54,000 years to reach Proxima Centauri. That's longer than recorded human history. That's before agriculture, before writing, before civilization. Voyager 1, launched in 1977 and now the most distant human-made object from Earth, is traveling at about 17 kilometers per second relative to the Sun. At that speed, it would take about 75,000 years to cover the distance to Proxima Centauri, assuming it were actually heading in that direction, which it's not. These aren't estimates or approximations. These are straightforward calculations based on known distances and velocities. And they reveal a fundamental truth. With any spacecraft we can currently build, interstellar travel takes tens of thousands of years. This isn't a technological challenge. This isn't a matter of building a bigger rocket or inventing a better engine. This is a confrontation with the sheer vastness of space, and it reveals that space is incomprehensibly, terrifyingly large. In August 2016, astronomers announced the discovery of a planet orbiting Proxima Centauri. They called it Proxima b, and it immediately became one of the most intriguing worlds ever discovered. The discovery was made using the radial velocity method, watching for the tiny wobble that a planet's gravity induces in its host star. Over 16 years of observations, using spectrographs at observatories in Chile and elsewhere, astronomers detected a periodic signal with a period of 11.2 days. The data suggested a planet with a minimum mass of about 1.17 times Earth's mass, making it potentially rocky like Earth, rather than gaseous like Jupiter. And crucially, its orbit placed it in the habitable zone, the region around a star where temperatures might allow liquid water to exist on a planet's surface. This combination Earth-like size, potentially rocky composition, possibly habitable temperatures made Proxima be an immediate target of fascination. Could there be life there? Could it be a second Earth? But we need to temper that excitement with realism. Proxima Centauri is a red dwarf star, much smaller and cooler than our Sun. For Proxima b to receive enough warmth to have liquid water, it must orbit very close to its star, only about 7.5 million kilometers away, compared to Earth's 150 million kilometers from the Sun. At that close distance, the planet is likely tidally locked, meaning the same side always faces the star, just as the same side of the Moon always faces Earth. This would create a permanent day side and a permanent night side, with extreme temperature differences that could make the planet hostile to life. Moreover, Proxima Centauri is a flare star. It regularly unleashes powerful stellar flares, bursts of radiation and charged particles far more intense than anything Earth experiences. Some of these flares are so powerful they temporarily double the star's brightness. If Proxima b has no magnetic field or thick atmosphere to protect it, these flares would sterilize the surface. Since the initial discovery, astronomers have found evidence for at least 2 more planets in the system. Proxima c, a larger world farther out, and possibly Proxima d, a smaller world even closer to the star than Proxima b. Each discovery adds complexity to the system. But here's what we don't know, and can't know with current technology. Does Proxima b have an atmosphere? If so, what's it made of? Does it have water? Is its surface solid, or is it shrouded in clouds? Does it have a magnetic field? Is there any chance, however remote, that it harbors life? To answer these questions definitively, we would need to send a spacecraft there. We would need to study the planet up close, analyzing its atmosphere with spectroscopy, mapping its surface, measuring its magnetic field, searching for biosignatures. And that brings us back to the fundamental problem: can we get there? Let's assess our current capabilities honestly. The Parker Solar Probe, launched in 2018, holds the record for the fastest human-made object. At its closest approach to the Sun, using the Sun's gravity to accelerate, Parker Solar Probe reaches speeds of about 163 kilometers per second relative to the Sun. That's extraordinarily fast. At that speed, you could travel from Los Angeles to Tokyo in less than a minute, but remember, space is vast. Even at 163 kilometers per second, Parker Solar Probe would take roughly 6,800 years to reach Proxima Centauri. 6,800 years. The pyramids of Egypt are about 4,500 years old. The entire span of recorded human history is only about 5,000 years. A mission at Parker's solar probe's maximum speed would take longer than all of human civilization has existed, and that's with no way to slow down. Parker achieves that speed by falling toward the Sun. To reach Proxima Centauri, a spacecraft would be moving away from the Sun, working against the Sun's gravity. It wouldn't naturally achieve anything close to 163 kilometers per second. More realistically, an interstellar probe using conventional propulsion might achieve speeds of 20 to 30 kilometers per second relative to the Sun, similar to Voyager 1's current velocity. At that speed, the journey to Proxima Centauri would take 40,000 to 60,000 years. But let's say we launch such a probe anyway. What challenges would it face? First, power. The RTGs that power Voyager and New Horizons decay over time. Voyager 1's RTG has lost about 60% of its initial power output since launch in 1977. At this rate, Voyager will lose the ability to power any instruments by the late 2020s, just 50 years after launch. For a 40,000-year journey, we'd need a power source that could last that long. We don't have one. Solar panels won't work in interstellar space. RTGs decay. Nuclear reactors require maintenance. There's no power source we can currently build that would function for millennia. Second, communication. At 4.24 light-years distance, radio signals would take 4.24 years to reach Earth. Send a signal, wait 4.24 years for it to arrive, wait another 4.24 years for a response. Any problem that requires Earth's help becomes an 8.5-year ordeal. But that assumes the spacecraft can still transmit with enough power to be received. As distance increases, signal strength decreases with the square of distance. Voyager 1 is currently about 23 billion kilometers from Earth, about 0.025 light-years. Its signal is already so weak it requires the most sensitive receiving antennas on Earth to detect. At Proxima Centauri's distance, maintaining communication would require either enormous transmitter power, which means more mass, which means more fuel, which makes the mission harder, or enormous receiving antennas, potentially kilometers across. Neither is currently practical. Third, navigation. A journey of 40,000 years offers no opportunity for course corrections. The slightest navigation error at the beginning compounds over time. Miss your target by 1 degree, and you'll be trillions of kilometers off course by the time you reach Proxima Centauri's distance. This would require navigation precision beyond anything we've ever achieved. And it would require the spacecraft to function autonomously for its entire journey, adjusting course based on its own measurements with no help from Earth. Fourth, the spacecraft itself. Electronics degrade, mechanical systems wear out. Cosmic radiation damages computer chips, micrometeorite impacts through road surfaces. The vacuum of space causes materials to outgas. Over decades, spacecraft require maintenance, which is why the International Space Station requires constant attention from astronauts and periodic resupply missions. A spacecraft designed to last 40,000 years would need redundancy upon redundancy, self-repair capabilities we haven't invented, and materials that don't degrade over millennia. We have no idea how to build such a thing. The honest assessment is stark. With current technology, interstellar travel is not just difficult. It's impossible in any practical sense. The journey takes longer than human civilization has existed. The spacecraft must function longer than any human artifact has ever lasted. And there's no way to control or assist the mission once it's launched. But perhaps future technology could change this. Let's examine that possibility. Over the decades, scientists and engineers have proposed numerous advanced propulsion concepts for interstellar travel. Let's examine the most serious of these proposals and assess their viability honestly. In the late 1950s, as nuclear technology was rapidly advancing and the space race was beginning, a group of scientists and engineers at General Atomics developed a radical concept called Project Orion. The idea was simple in concept but staggering in execution. Propel a spacecraft by detonating nuclear bombs behind it. The spacecraft would have a large pusher plate, essentially a shock absorber. Each nuclear explosion would strike the plate, and the spacecraft would absorb the momentum and accelerate forward. It sounds insane, and in many ways, it is, but the physics work out. Nuclear bombs release enormous amounts of energy. If you could harness even a fraction of that energy for propulsion, You could achieve accelerations and velocities far beyond what chemical rockets can provide. Project Orion's designers calculated that such a spacecraft could theoretically reach speeds of 3% to 5% of the speed of light. At those velocities, a trip to Proxima Centauri would take 85 to 140 years. Still a long time longer than a human lifetime, but within the realm of conceivability. You could potentially have a multi-generational mission where the crew's grandchildren would arrive at the destination, so why didn't we build it? First, the Partial Nuclear Test-Ban Treaty of 1963 prohibited nuclear explosions in space. The environmental and political opposition to launching thousands of nuclear bombs, even for peaceful purposes, was and remains insurmountable. Second, the engineering challenges were formidable. The pusher plate would need to withstand thousands of nuclear explosions. The spacecraft would need to carry thousands of nuclear devices. The mass of the entire system would be enormous. Some designs called for spacecraft massing thousands of tons. Third, and perhaps most importantly, even if we solve the technical and political problems, nuclear pulse propulsion still faces the fundamental limitation of reaction mass. You can only carry so many bombs. Once you've used them all for acceleration, you have nothing left for deceleration. You'd arrive at your destination at 3% to 5% the speed of light, with no way to slow down. Project Orion was cancelled in 1965. Occasional revivals of interest have occurred over the decades, but no serious effort has been made to actually build such a spacecraft. The political obstacles alone make it essentially impossible, regardless of the technical feasibility. Modern reassessments suggest that even if every obstacle were overcome, nuclear pulse propulsion would still result in century-long missions to the nearest stars. It's not a solution to interstellar travel. It's just a way to make it slightly less impossible. Nuclear fusion, the process that powers the Sun and other stars, offers a more elegant approach in theory. Fusion releases far more energy per unit mass than fission. If we could build a rocket engine powered by fusion, it could theoretically achieve much higher exhaust velocities than any chemical rocket, improving efficiency dramatically. One particularly interesting concept is the Bussard interstellar ramjet, proposed by physicist Robert Bussard in 1960. The idea is to collect hydrogen atoms from interstellar space using a massive magnetic scoop, then fuse them to generate thrust. In principle, this would eliminate the need to carry fuel. The spacecraft would collect it as it goes. It's an elegant concept. And if it worked, it would solve one of the fundamental problems of space travel: the need to carry your fuel with you, which creates the exponential mass problem of the rocket equation. But there are fatal flaws. First, interstellar space, while not a perfect vacuum, is extraordinarily empty. There's roughly 1 hydrogen atom per cubic centimeter. To collect enough hydrogen to power a fusion reaction at any meaningful rate, you'd need a magnetic scoop hundreds or thousands of kilometers across. The engineering challenges of building and maintaining such a structure are overwhelming. Second, and more fundamentally, detailed analysis has shown that at the velocities where a ramjet would need to operate, the drag from collecting the interstellar hydrogen would exceed the thrust generated by fusing it. In other words, the ramjet would slow you down, not speed you up. It's like trying to power a car by scooping up the air resistance in front of it. The concept doesn't work. Third, and perhaps most damning, we still haven't achieved controlled nuclear fusion for power generation after more than 70 years of research. ITER, the International Thermonuclear Experimental Reactor currently under construction in France, aims to achieve sustained fusion reaction sometime in the 2030s, but even if successful, it will only demonstrate that fusion can generate more energy, and it consumes the so-called break-even point. Building a fusion reactor small enough and efficient enough to power a rocket is still many decades away, if it's possible at all. Fusion rockets remain theoretical. We have no working prototype. We have no clear path to building one, and even if we solved all the physics and engineering challenges, the best fusion rocket designs still predict journey times to Proxima Centauri measured in centuries. It's not a practical solution. It's a concept on paper that may never become reality. If you want maximum efficiency in converting mass to energy, antimatter is the answer. When matter and antimatter collide, they annihilate completely, converting all their mass to energy according to Einstein's famous equation E equals mc. No other reaction is more efficient. It's 100% conversion of mass to energy. A rocket powered by matter-antimatter annihilation could theoretically achieve exhaust velocities approaching a significant fraction of the speed of light. Some designs suggest speeds of 50% to 70% of light speed might be possible. At those velocities, a trip to Proxima Centauri could take as little as 6 to 12 years, fast enough that a human crew could make the journey within their lifetime. So why aren't we building antimatter rockets? The problems are, quite simply, insurmountable with any foreseeable technology. First, production. We can create antimatter. Particle accelerators, like those at CERN, produce antiparticles regularly. But the quantities are infinitesimally small. In the entire history of antimatter production, we've created roughly 20 nanograms, 20 billionths of a gram. That's the mass of about 10 million atoms. To power an interstellar mission, you'd need kilograms of antimatter. That's not a million times more than we've made, it's trillions of times more. Second, cost. Current antimatter production costs are estimated at about $62.5 trillion per gram. That's trillion, with a T. To produce even a single kilogram would cost $62.5 quadrillion, roughly 600 times the entire GDP of Earth. Even if we improve production efficiency by a factor of 1 million, it would still cost tens of billions of dollars per gram. And remember, you'd need multiple kilograms for a meaningful mission. Third, storage. Antimatter cannot touch regular matter, or it annihilates instantly. Storing antimatter requires perfect magnetic or electric containment, suspending the antiparticles in a vacuum with no contact with any surface. The largest quantities ever stored lasted for minutes to hours before being lost. Storing kilograms of antimatter for years, the duration of even a fast interstellar mission, would require containment systems you have no idea how to build. Any failure would result in instant annihilation of the antimatter, releasing energy equivalent to multiple nuclear bombs. Fourth, energy requirements. Creating antimatter requires energy. In fact, it requires far more energy than you get back when the antimatter annihilates. The process is hideously inefficient. To create enough antimatter for an interstellar mission would require dedicating the total energy output of human civilization for multiple years. And even if somehow we overcame all of these obstacles, antimatter propulsion still faces a fundamental limit: the reaction mass problem. You're accelerating by throwing mass out the back of your spacecraft. Eventually, you run out of mass to throw. And unlike the Bussard ramjet, there's no way to collect more fuel in interstellar space. Antimatter propulsion is not impossible in the sense of violating the laws of physics. But it's impossible in every practical sense. The technological and economic barriers are so vast that calling it impossible is more honest than calling it difficult. In April 2016, physicist Stephen Hawking and investor Yuri Milner announced the Breakthrough Starshot initiative. It was, and remains, one of the most serious proposals for interstellar travel ever developed. The concept is to build thousands of tiny spacecraft, each weighing just a few grams, equipped with light sails. These spacecraft would be launched into space, then accelerated to 20% the speed of light using powerful lasers based on Earth. At 20% light speed, the journey to Proxima Centauri would take roughly 20 years. Add another 4.24 years for signals to return, and you could potentially have data from Proxima be within a human lifetime, about 25 years after launch. The concept has several advantages. By keeping the spacecraft incredibly small, just a few grams, you avoid the tyranny of the rocket equation. The propulsion system stays on Earth, so you don't need to carry fuel. And light sails have been successfully tested in space, proving the basic principle works. So is this the solution? Can we finally reach another star? Not so fast. Let's examine the challenges honestly. First, the laser array required would be enormous. We're talking about lasers with a combined power output of about 100 gigawatts, comparable to the output of 100 nuclear power plants. These lasers would need to be precisely aimed and coordinated to push the tiny sail for several minutes during the acceleration phase. The cost of building such a laser array is estimated at $5 to $10 billion. That's just for the lasers, not including the spacecraft themselves, the mission operations, or the receiving equipment needed to detect the incredibly weak signals the probes would send back. Second, the spacecraft can only carry a few grams of payload. That's enough for a camera, some basic sensors, and a tiny transmitter. It's nowhere near enough for the kind of comprehensive scientific instruments you want for studying another planet. Third, and critically, you can't slow down. At 20% the speed of light, the spacecraft would fly through the Proxima Centauri system in a matter of hours. There would be no orbiting, no extended observation, just a very fast flyby, during which the spacecraft would need to collect all its data and begin transmitting immediately. Fourth, navigation is nearly impossible at these speeds. Space isn't perfectly empty. There are dust grains, stray atoms, even the occasional larger particle. At 20% the speed of light, a collision with even a tiny dust grain releases enormous energy enough to destroy the spacecraft completely. Shielding is impractical because any shielding adds mass, which defeats the purpose of keeping the spacecraft tiny. So the spacecraft would essentially be running a gauntlet through interstellar space, with no ability to steer around hazards. Fifth, communication is problematic. A few-gram spacecraft can only carry a tiny transmitter. By the time its signal reaches Earth from 4.24 light-years away, it would be extraordinarily weak, possibly too weak, to detect even with our most sensitive instruments. Breakthrough Starshot has received some funding for early research, but there's no timeline for actually building and launching the system. The challenges are formidable, and many scientists question whether they can all be overcome. My assessment, Breakthrough Starshot represents the least impossible approach to interstellar travel that we've conceived. But least impossible is not the same as possible. It's a concept that might, with significant breakthroughs in laser technology, material science, and communications, succeed in sending a tiny probe on a fast flyby of another star system within this century. But it's not a solution to human interstellar travel. It's not even a solution to sending comprehensive robotic missions. It's the absolute minimum possible achievement, sending a camera a high-speed pass through another star system, with no guarantee it will survive the journey or that we'll receive its data. And even that minimum achievement would require technological development and investment on a scale that may not happen. Let's talk about energy in concrete terms, because this is where the impossibility of interstellar travel becomes most stark. The kinetic energy of a moving object is given by the equation 1/2 times mass times velocity squared. That squared term is critical. Double your velocity, and you quadruple the energy required. Increase velocity by a factor of 10, and energy increases by a factor of 100. Let's calculate the energy required to send a 1-ton spacecraft 1,000 kilograms to 10% the speed of light. That's 30,000 kilometers per second. The kinetic energy is 1/2 times 1,000 kilograms times 30 million meters per second squared. That equals 4.5 times 10 to the power of 17 joules. How much energy is that? Let me put it in perspective. Total human energy consumption in 2023 was approximately 580 exajoules. An exajoule is 10 to the power of 18 joules. So to accelerate our 1-ton spacecraft to 10% of light speed would require about 45% of humanity's total annual energy consumption. Not 45% of our electricity, not 45% of our transportation energy. 45% of all energy humanity uses in an entire year: electricity, transportation, heating, industry, everything. And that's just for acceleration. If you want to slow down when you arrive, you need the same energy again. So we're looking at roughly 90% of humanity's annual energy output just to send 1 ton of spacecraft to another star. Remember, that's 1 ton. New Horizons was about 1/2 ton. The Voyager spacecraft were 3/4 of a ton. These are tiny spacecraft carrying minimal instruments. A spacecraft capable of comprehensive scientific study or carrying humans would need to mass much more. Multiple tons at minimum, tens or hundreds of tons for a crewed mission, and the energy requirements scale linearly with mass. A 10-ton spacecraft requires 10 times the energy. A 100-ton spacecraft requires 100 times the energy. We're talking about dedicating multiple years of humanity's total energy output to send a single mission to the nearest star. That's not just expensive or difficult. That's a civilization-level commitment that would require redirecting vast swaths of the global economy toward a single goal. And even if we decided to make that commitment, there's another problem. We don't have any way to actually deliver that energy to the spacecraft efficiently. Chemical rockets are only about 65% efficient. Ion drives are better, but still require reaction mass. Even antimatter, theoretically 100% efficient, would require us to first spend even more energy creating the antimatter. There's no free energy in space. Every joule has to come from somewhere. And the universe doesn't give discounts on the laws of thermodynamics. Let's say we somehow solved the energy problem. Let's say we develop propulsion systems that could accelerate a crewed spacecraft to a significant fraction of light speed. What then? Even with optimistic propulsion technology, an interstellar mission would take decades at minimum. More likely, we're looking at journeys measured in generations. A trip to Proxima Centauri at 10% light speed would take 42 years, one way. At more realistic speed, say, 1% light speed, which is still far beyond our current capabilities, we're looking at for 120 years. This introduces biological and psychological challenges that are arguably more insurmountable than the physics. For a multi-generational mission, you need a viable population. Population genetics studies suggest you need at least 50 people for short-term genetic viability, and preferably 500 or more for long-term sustainability across multiple generations. This eliminates genetic problems from inbreeding and provides sufficient genetic diversity for the population to remain healthy. So we're not talking about sending a handful of astronauts. We're talking about sending a small community. And that community needs to be completely self-sufficient for decades or centuries. The life support systems alone are staggering to contemplate. You need to recycle everything: water, air, nutrients. You need to grow food. You need medical facilities capable of treating any illness or injury without access to Earth's hospitals. You need to maintain genetic diversity through careful breeding programs. You need to handle births, childcare, education, and eventually, deaths and disposal of bodies. You need to maintain technology over multiple generations. Ship systems will require repair and maintenance. Who trains the engineers if the original crew dies? How do you ensure knowledge and skills are passed down across generations? And then there are the psychological challenges. Human beings evolved to live on Earth's surface with open horizons, natural light, weather, seasons. Confining people to a spacecraft for their entire lives, with no possibility of leaving, no possibility of returning to Earth, raises profound questions about mental health. Studies of isolated populations, Antarctic research stations, submarines, the International Space Station show that humans can tolerate confinement for limited periods. But entire lifetimes, multiple generations? We have no data on this because it's never been attempted. We don't know if it's even psychologically possible. Then there's radiation. Earth's magnetic field protects us from cosmic radiation and solar particles. In deep space, there's no such protection. Spacecraft shielding can help, but adding more shielding adds mass, which increases energy requirements exponentially. Long-term exposure to cosmic radiation increases cancer risk, damages DNA, and potentially causes neurological problems. For a journey lasting decades, the cumulative radiation dose would be significant, even with shielding. For a multi-generational journey, you might have people dying of radiation-induced cancers before the ship even reaches its destination. And finally, there's the gravity problem. The human body needs gravity. Astronauts on the ISS lose bone density and muscle mass despite rigorous exercise regimens. For trips lasting years or decades, this becomes a serious problem. You could potentially solve it by rotating the spacecraft to create artificial gravity, but that adds engineering complexity and mass. The honest assessment is that human interstellar travel doesn't just require solving the propulsion problem, it requires solving biology. We would need to either develop technology to extend human lifespans dramatically, or accept that interstellar travel means sending people who will never reach the destination. They're merely the ancestors of those who will arrive. And that raises profound ethical questions. Is it moral to confine people to a spacecraft before they're born, giving them no choice in the matter? Is it moral to send people on a journey they can never abandon, knowing they'll die in transit? These aren't engineering questions, these are philosophical questions. And they may present barriers just as insurmountable as the physics. There's one more fundamental barrier we need to discuss: the speed of light as a communication limit. Light is fast, it's the fastest thing possible according to physics. But even at light speed, distances in space create enormous communication delays. At Proxima Centauri's distance of 4.24 light-years, a radio signal takes 4.24 years to travel from the spacecraft to Earth. Send a message today, and Earth receives it in 4.24 years. They respond, and you receive their response in another 4.24 years. Total round-trip time, 8.5 years. Let me illustrate why this is a problem with a scenario. You're on a spacecraft approaching Proxima Centauri. A critical system fails, let's say life support. You immediately send a distress signal to Earth, describing the problem in detail. That signal travels at light speed toward Earth for 4.24 years, while you re-dealing with the failing system using only the resources and knowledge on board. Finally, 4.24 years after you sent the distress signal, it reaches Earth, Mission Control receives it, analyzes the problem, consults with engineers, and develops a solution. They send detailed instructions back to you. That message travels at light speed toward your spacecraft for another 4.24 years. Finally, 8.5 years after the initial failure, you receive the solution from Earth, but by then, the problem has evolved. Your stopgap fixes have had their own consequences. Maybe the failing life support has damaged other systems, maybe you've lost crew members. Maybe the situation is now completely different from what you described 8.5 years ago. This is the communication problem. Mission control, as we understand it from decades of space missions, becomes impossible. The spacecraft must be completely autonomous. Every decision must be made on board with no help from Earth, and it's not just emergencies. It's everything. Scientific discoveries can't be shared with Earth in real time. Course corrections can't be coordinated with ground control. If the spacecraft encounters something unexpected, it has to deal with it alone. This also means that the spacecraft's systems must be extraordinarily reliable. There's no cavalry coming. There's no resupply mission. There's no emergency return to Earth. Whatever you launch with is all you have for the entire mission duration. For a mission lasting decades or longer, this requirement for complete autonomy and perfect reliability is extraordinarily demanding, and it gets worse the farther you go. Proxima Centauri is the nearest star. Most stars are much farther. Send a mission to a star 50 light-years away, and the communication delay becomes 100 years round trip. Your great-grandchildren might receive the response to a message you sent. This isn't just inconvenient, it fundamentally changes what's possible. It means interstellar spacecraft must be autonomous to a degree we've never achieved, and it means that from the moment of launch, the mission is essentially on its own. Earth can watch and listen, but we cannot meaningfully help. Everything we've discussed, the energy requirements, the timescales, the biological challenges, the communication problems, leads to an uncomfortable possibility. The Fermi paradox asks, where is everybody? Given the vast number of stars in our galaxy, and the apparent ease with which life can arise given the right conditions, we might expect the galaxy to be teeming with civilizations. Yet we see no evidence of any. No radio signals, no megastructures, no signs of galactic colonization, nothing but silence. One possible answer is the Great Filter hypothesis. This suggests that there's some barrier, some filter, that prevents civilizations from spreading across the galaxy. Something that is extremely difficult or impossible to overcome. The question is, where is that filter? Is it behind us? Perhaps the origin of life itself is extraordinarily rare, and we're lucky to exist at all. Or is it ahead of us, something that will prevent us from expanding beyond our solar system? What if interstellar travel is the great filter? What if the laws of physics simply don't permit practical interstellar travel? What if every civilization, no matter how advanced, runs into the same barriers we've discussed? The energy requirements, the time scales, the impossibility of maintaining a civilization-level commitment for centuries or millennia. We've looked at advanced propulsion concepts: nuclear pulse propulsion, fusion rockets, antimatter, light sails. None of them provide a practical path to interstellar colonization. They might allow sending tiny probes on long-duration missions. But colonization, settlement of other worlds around other stars, that might simply be impossible, and if it's impossible for us, it's probably impossible for everyone. Physics is universal. The laws that constrain us constrain any alien civilization. The energy requirements don't change based on how technologically advanced you are. The speed of light limit doesn't get negotiated away through clever engineering. This could explain the Great Silence. Not because aliens don't exist, not because civilizations destroy themselves before reaching the stars, but because reaching the stars is fundamentally impossible for biological beings confined to planets. We might live in a galaxy filled with civilizations, each trapped in their own solar system, aware of each other through radio signals, but forever unable to meet. Islands of consciousness in an ocean of space too vast to cross. This is, in many ways, a depressing thought. The human spirit yearns to explore, to expand, to reach for the stars. The idea that we might be permanently confined to our solar system feels like a defeat, but it might also be liberating. If interstellar travel is impossible, then we don't need to feel bad about not achieving it. We don't need to compare ourselves unfavorably to imagined aliens who've supposedly cracked the problem. We can accept our limits and focus on what we can do. And that brings us to our final section, perspective. So here we are, we've examined the physics. We've calculated the energy requirements, we've assessed the technological challenges, and the conclusion is unavoidable. With anything resembling current technology, and even with advanced technologies we can theoretically envision, interstellar travel ranges from impractical to impossible. Does this mean we're trapped? Is our solar system a prison? I think the answer depends on perspective. Science fiction, from Star Trek to Star Wars to countless novels and films, has given us a vision of humanity spreading across the galaxy, visiting countless worlds, meeting alien civilizations. These stories are compelling and inspiring. They capture something essential about human nature, our drive to explore, our curiosity about what lies beyond the horizon. But they're fiction, they're stories, and they've shaped our expectations in ways that may not be realistic. The universe is not obligated to be the way we want it to be. The laws of physics don't bend to accommodate our dreams. And the honest truth is that space is big, empty, and mostly hostile to life. The distances between stars are so vast that they might as well be infinite for practical purposes. This doesn't make us trapped, it makes us special. Life intelligent, technological life is rare enough that we haven't detected any others despite decades of searching. And if life is rare, and interstellar travel is impossible, then Earth might be the only place in hundreds or thousands of light years where conscious beings exist to contemplate the universe. That's not imprisonment, that's responsibility. If Earth is the only place where life has achieved consciousness and technology, then protecting Earth becomes paramount. There's no backup planet. There's no escape hatch. This is it. But it's also opportunity, because while interstellar space may be beyond our reach, our solar system is not. And our solar system is vast, diverse, and largely unexplored. Let's talk about what's actually achievable with current or near-future technology, because this is where the real excitement lies. Mars is difficult, but possible. It's a 3 to 6 month journey with current propulsion systems. We've successfully landed multiple rovers there. We've studied its atmosphere, its geology, its potential for harboring past or present life. Sending humans to Mars would be expensive and risky, but it's within our capabilities if we choose to commit the resources. The asteroid belt contains millions of bodies rich in metals and other resources. Mining asteroids for resources, particularly water, which can be split into hydrogen and oxygen for fuel, could enable sustained human presence in the inner solar system. This isn't science fiction. Companies are actively developing asteroid mining technology. Jupiter's system contains some of the most intriguing targets in the solar system. Europa, with its subsurface ocean beneath an ice shell, could potentially harbor life. We're planning missions to study it. Ganymede, the largest moon in the solar system, also shows evidence of a subsurface ocean. Callisto, pockmarked with ancient craters, tells the story of the solar system's violent early history. Saturn's moons are even more extraordinary. Titan, larger than the planet Mercury, has a thick atmosphere and lakes of liquid methane on its surface. It's the only world besides Earth with stable liquid on its surface. NASA's Dragonfly mission, scheduled to launch in the 2020s, will send a robotic rotorcraft to explore Titan's surface. Enceladus, tiny but geologically active, shoots geysers of water from its South Pole, water from a subsurface ocean that might support microbial life. These are real targets, places we can reach. Places that might answer the profound question, are we alone?